Okay, so today we are going to sort of very briefly mention some applications. Before that, I have to I have promised that I would write down the general formula for the Weil dimension formula. Let me quickly write that. So that formula is the following. That formula is the following, that so suppose that you have some highest weight state which is being thought of as a vector. Okay, is given by a highest weight vector which is lambda. So that's a vector in some r dimensional space, as we have always been doing. And let us say that this lambda is given by some numbers. So remember that so these are some integers. These are called Dynkin labels. Jesus. These are called Dynkin labels. Dynkin labels. So remember that these basically give you the depth of the towers along the various simple root directions. And let me also introduce another notation, that an arbitrary positive root, okay, is written, of course, as an integer linear combination of the simple roots. And I would call those numbers, these are non-negative numbers, I would call these things as Ki alpha. Okay. Then the dimension formula is the following. So the dimension of the representation space given by the highest weight vector lambda. Remember that once I specify the highest weight vector, I have specified the representation, okay? Because we have discussed how to and here now, so this is there's a product over all positive roots of the following quantity. Sum over I this is the Weil dimension formula. So this is called the dimension formula. Okay. And right. So there are as I mentioned, that there are these A, D and E type of Lie algebras for which these double bonds and triple bonds do not appear in the root diagram. For them, these alpha I, these norms of these root vectors are all equal, and you can take them to be 1. So for them, this and this just cancels out, and so for the A, D, E type of Lie algebras, in particular A is the SUNs. So for them, it just becomes alpha all positive roots and Ki alpha sum over I divided by Ki alpha. Okay. So now let's check out for SU3 what's the story. So for SU3, let us say, so remember that for SU3 this is how it was, that there were two roots, alpha 1 and alpha 2, and the positive roots were alpha 1, alpha 2 and alpha 1 plus alpha 2. Okay. Those are all positive roots, and so there are 3 positive roots, 3 negative roots and 2 Cartan subalgebra elements. So that gives you the 8 generators, and so that's what it is. And so therefore, this guy, what are the ki alpha integers for alpha 1? It's just 1 and 0. Okay, so this, so the k guys are for this is 1 0, this is 0 1, and this is 1 1. So these are the k vectors for these various positive roots. Okay. Good. And now let us look at the sum highest weight, which is given by m1, m2, okay, which I have called here lambda 1 and lambda 2, right. So now the dimension, so we look at the product over all possible positive roots. So let us look at the case in which I take this term for alpha 1, right. So that will be from here I'll get, so ki alpha is just 1 comma 0, 1 comma 0. So if you work it out, is quite clear. That is m1 plus 1 1 dot that divided by 1. So this is the contribution coming from alpha 1. Okay. So I'm now looking at the alpha 1 term of this. So only one I clicks. Okay, that's I equal to 1. So and lambda 1 becomes m1, and this is just 1. So that's what I did. Next term is the contribution from alpha 2, and that is the now only the I equal to 2 term contributes here, and that's 1. So 1 times m2 plus 1, and here it's just sum over all possible k's, that also is 1, like that. Okay, now the contribution of alpha 1 plus alpha 2, the vector now is 1 1. So that you have to do here. So it's 1 into m1 plus 1, that's I equal to 1 element, plus 1 into m2 plus 1 divided by 1 plus 1. So that's the m1 plus 1, m2 plus 1, m1 plus m2 plus 2 divided by 2. So that's the formula that we had quoted last time. And of course, in the case of SU3, we had an independent combinatorics argument for this using the Young tableau or the tensor representations. Okay, so that's what it is. And for SU4, also you can do this drill, for which the other roots will be alpha 1 plus alpha 2, and alpha 2 plus alpha 3, and alpha 1 plus alpha 2 plus alpha 3. So there are 3 simple roots and 3 other positive roots, and you can arrive at the SU4 formula which we wrote down in class. Okay, so this is the and just for fun, let's work out SU2. Okay, so there is only one root, that's alpha, and of course there is only one positive root, and that has the k vector, which is also equal to just 1. So the k vector is just 1. Okay, so if you apply and the Dynkin label, for a spin J representation, can anybody say what the Dynkin label is? So lambda 1, okay, which you might also call M1. What is the Dynkin label for a spin J representation? What does it mean? A Dynkin label means that starting from the highest weight state, how far down can I go? 2j plus 1 is the full thing, but starting from there, the depth of the tower is 2j. Okay, so therefore, this is 2j. Okay, now let's apply to this. So there's only one contribution, which is 1 plus m1 plus 1 divided by 1. Okay, so that of course is our famous friend, which is 2j plus 1. So the Weil dimension formula gives you 2j plus 1. Not that you needed this formula to arrive at this, but that's what it is. Okay, so that finishes that part of our thing. And let me just now much of this is, so I will rest assured make an assignment with help about the application part. Okay, so I will basically mention some of these applications. So first I'll talk about some things about atomic physics, and then I will also talk about something like quark physics. And it will not be in great gory detail, but the details you should fill up in, and then there will be also something about gauge theories, gauge symmetries versus global symmetries, and so on and so forth, but I'll put them in assignments. All right, so let's do some atomic physics now. So hydrogen. So just we go back to the hydrogen atom, and remember that we already said this, that the hydrogen atom is it has, so this is in the approximation in which the proton is infinitely massive, and so therefore there is only one degree of freedom, which is the electron, and it's in the central force potential. So there is a SO3 symmetry, and therefore the spectrum would look like this. This is the energy axis, and the spectrum should look like, so there should be degeneracies, okay, in the Hamiltonian. So what is the idea? So I'm saying that the Hamiltonian commutes with all the generators of SO3 or SU2, because we are talking about Lie algebra here. So so it's like E alpha for all alpha equal to 0, H E minus alpha equal to 0. So I'm using Cartan subalgebra. In this case, this is just J plus, J minus, and J3, okay, or L plus. So excuse me, because I'm talking about now orbital angular momentum. So therefore, irreps of the SU2L, the orbital, okay, they would form degenerate subspaces of the Hamiltonian. So this is how it goes, and we already know what they are like. So now if I also include the spin, okay, so the non-relativistic Hamiltonian does not depend on spin at all, okay. So therefore, there's, if you wish, one is plus and one is minus, okay, where plus and minus are the two spin doublets, okay. So there's the degeneracy of 2, and then I have 2s plus 2s minus, and degenerate with that there will be 2p z and 2p plus 2p minus. This we have already been through, and 2 giving the spin quantum numbers. And so you can derive from the degeneracy from the dimension formula for the various irreducible representations. You can find the magic numbers of the principal quantum number corresponding to 1, 2, 3, 4, blah blah, etc., etc. So we will get 2n square. Okay, so there should be 2n square number of eigenstates here. There should be 2n square number of eigenstates here, etc., etc. All right. That is left as an exercise. I hope I am saying the number right. I don't know where I wrote this, but it is 2n square, isn't it? Yeah. So at any n, it is 2n square is the degeneracy. Okay. Now I consider yes.
Just by those condition relations, we can't say that the 2s and 2p should have the same energy.
Thank you. That's right. Just by this commutational relation, I cannot have that. So indeed, in principle, yes, absolutely. So these guys could have different energies. So that's something special about the 1 over r potential. So that has an extra symmetry as a result. Thank you. So that's a good. I unfortunately I don't have time to go into that extra symmetry. It has actually an SO4 symmetry. This 1 over r potential, and because of the existence of some additional conserved quantity other than the angular momentum, so it enhances the symmetry from SO3 to SO4, and that is the reason why the 2s and 2p appear. Thank you for pointing that out. Okay, good. So anyway, now the what I wanted to say is that what happens if you have multi-electron, if you have a multi-electron system. Okay, and the first thing that you find is that because of many of you already know what the story is. So let us say you have 2 electrons. You have 2 electrons. Anybody has an idea of such an atom? Okay, so I presume that people know this. Of course, that's oxygen. No? All right, it's not oxygen, it's something else. What is it? With 2 electrons? What? Helium. Okay, good. Okay, so what happens is that because of the fact that electrons are fermions, okay, you have to ensure that it's antisymmetric under exchange of quantum numbers, the electron wave function. As a result, there is an exchange interaction that comes into play. Everybody is familiar with this? Yeah? Okay. So this was first found by Dirac, and you can find some lovely discussion of this exchange interaction. Much like you can find a lovely discussion of anything in Landau-Lifshitz. So you can look it up, and what happens is that this gives rise to, so now let's say 2 electrons. So that story, this story was for just the hydrogen atom, single electron. So now we have, you know, like, let me say that the two electrons are given by position coordinates, which are R A, where A runs. So in general, P electrons, let's say there are P electrons, 1, 2 up to P. And what's the potential? Now there's a two-body potential. The one-body potential remains the same. All these electrons are in the external central potential of this thing. So, but now there is also this. Like that, and A less than B. Okay, so there are these potentials. I'm not writing the constants here. So and the one body potential continues to be 1 over R A, sum over A, and of course there's a kinetic energy. Kinetic energy, which is minus del square del R A square, sum over A. Okay, I'm not writing any constants at all. E, H bar, M, C, anything. Good. So is there some symmetry now of this system, of this dynamics? Permutation symmetry, yes, but is there a continuous symmetry at all, or have I killed it all by this? Rotational symmetry is still there. Everybody gets rotated exactly by the same way. So this is still a symmetry, where this R is the rotation matrix, which applies to all. So for all A, it's the same R. Okay. Any idea about what is the generator for this symmetry? So earlier, so that you have to derive. Okay. So for R, you know, take a infinitesimal rotation, let's say about the z-axis, and find it out, etc., etc. But what you will find is that so it is like the following, that x, so Li is equal to epsilon I j k x a I del x a, sorry, excuse me, j k, and well, minus I don't have to write. So this, well, modulo factors of half or something, which I'm not being careful about. So maybe I can write that other guy also. No, that's it. Okay. This is the thing which rotates just the eighth particle. Okay. Now the sum over A is coming. Okay. So this, if you wish, is Lia, but that's not a symmetry. Okay. That does not commute with the Hamiltonian, but this one does. So sum over all angular momentum operators. Okay. So once I have introduced terms like these, okay, so the independent what could have been SO3 cross SO3 cross SO3 is the independent SO3s for all of them. Okay. This breaks that symmetry of so many copies of SO3 into a single copy of SO3.
So
and
this
that's
is for any potential that's a function of the distance between the two particles.
That's right. So there is a two-body potential, which of course still respects the fact that it's mod of the whatever. Okay. So now, interestingly, this has a group theoretic significance, namely that this summation. Okay. So now, suppose that I want to write down the joint wave function of all these particles. Okay. So part of it will be some radial coordinate, and part of it will be the angular coordinates. Okay. Now, in other words, what I am saying is that you can imagine constructing representations of each of these LIAs, okay, out of the first particle. Okay. And then what the full wave function would be like a tensor product of all the, let's say, I can have the the spherical harmonics built out of each of these angles. Okay. Now, so what I'm saying is the following, that so this is for particle 1. Suppose this guy was not there. Okay. Then I would write some sort of spherical harmonics for the first guy. Okay. Then I would write some spherical harmonics for the second guy, etc. So these will all be given by some y L1 M1, okay, times some radial function, and this will be given by some y L2 M2, blah blah. Okay, up to I'll call the total number of particles as P, like that. Okay. Now I have turned on this guy. Okay. As a result, these should be rather split in terms of the final conserved quantity, okay, which is the sum of all these angular momentum operators. That is the final conserved quantity. Okay. So you better do a tensor product decomposition of each of these guys in terms of the total angular momentum. Is that clear? So that's what you do. So you have these in terms of the this kind of thing. It's some number of boxes, and then some number of boxes here. Etc. etc. So this is the tensor product of this is the tensor product of irreducible representations like this, and these guys can be written in terms of the standard Clebsch-Gordon rules and whatnot. Okay. The point that I wanted to make to you is that this is what we have called the angular momentum. Okay. And Li acting on these objects. Okay. So what I mean is that this is Leibniz rule. This sum is really like Leibniz rule. So this is how the angular momentum operator. So if you think of this as a representation of SU2, this as the representation of SU2 or SO3, whatever, this as a representation of SU2, the same SU2. Okay, then that SU2, so this one single SU2, okay, so that SU2 generator will act on this product wave function. How? It will act by Leibniz rule. It will first act on this one and not on these, etc., 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 and this summation is just that. Is that clear? Okay. In terms of eigenvalues, you can see that right away, that if you just look at the J3 or L3 operator, then the L3 operator has an eigen value on this, which is M1. This has a thing which is M2, etc., etc., and the whole thing will be given by M1 plus M2 plus M3, etc. But that is given by our the discussion that we had so far, that you have a tensor product decomposition of some group, okay, and the Cartan subalgebra elements, okay, just pick up the sum of those eigenvalues because of the Leibniz rule prescription for how the Lie algebra generators act on a product wave function. Okay. So, this is just that. Okay. All I am trying to say here is that there is only one SU2 that is operative on all of these. So, whatever we have said before can be physically applied to this situation. Okay, good. So, that is point number 1, and the other thing that happens, here is that so if this is the only thing that happened, then the total angular momentum of all these p electrons is given by so here this is how the quantum numbers are written for the hydrogen atom, L, Ml and Ms if you wish, and well, you could say that this is L, Ml, Lm and S, Ms, but this S is half. Okay. These are the electron eigenstates in a hydrogen atom. Now, so let us say that I have I have taken some. So okay, so I'm not going to sort of belabor the point that so there will be some representation 2L plus 1 dimensional representation, okay, of coming from all this tensor product. You will have various kinds of L values with 2L plus 1 dimensional irreducible representations, okay, each of which will be degenerate, okay, So, now the story will be something like that it will be given by the capital L values. So, capital L values and the degeneracy would be 2L plus 1, okay. And of course, there could be some notion like a principal quantum number, several such quantities. So, it will be given by L value and of course, there is an ML, okay. So, L is the if you wish the highest weight of this representation. So, that is the like the L3 value of the the third component of the angular momentum on the highest weight vector, that is L, and then ML is the specific state. So, the number of such MLs is 2L plus 1, and there would be also an total spin. Okay, so, I have not said anything about spin so far. You might say that, well, if there are p number of electrons, okay, something is happening because of this interaction, so that I should pick out the total L, okay, as the possible eigenstates of the Hamiltonian, the total L, not the individual L's as before. And the spins can do what they like, So, for every electron it could be plus or minus, etc., etc. So, as a result it would be how many such possibilities are there? For p electrons I can take plus or minus, etc., etc. Okay. So, what's the total number? So, that is 2 to the power p. Okay. So, that is 2L plus 1 into 2 to the power p is what you would think, okay, but that is actually wrong. Why is that wrong? because although I haven't said it, there is another term which appears in the thing, that's called exchange interaction. Okay. So what is the deal? Let's go to 2 electrons. So you probably already know this, right? Do you know what this object is, the exchange interaction? Let me just say it very quickly. So this is what any I think everybody knows this exchange interaction or not. Okay, let me just say it. Okay, this is how the wave functions look like. Okay, and and let us say that I have some two-body interaction like that. Okay, so V1, 2, and okay, this is the full term in the action that appears. Okay, so this V is a function of R1 minus R2, let's say. Okay, so so there are of course sensible terms here which are like phi 1 R1 mod square, phi 2 R2 mod square, which is like a density and V R1 minus R2. Okay, and that's like the normal kind of interaction. But there are cross terms here which are of the following kind, that it is like phi 1 R1 and phi 1 bar R2 and phi 2 R2 and phi 2 bar R1, like that. Okay, so as if half of the particles are at R1 and the rest of so it's like these two. Okay, I rubbed it off, but it's like a mixed exchange, in which the particles have flipped their positions. Okay, so instead of phi 1 bar at R1, which would have had a natural classical understanding, okay, here phi 1 bar of R1, okay, and phi 2 bar of R2, they have changed their locations. Okay, they have flipped, they have exchanged their locations, and this does appear in the potential energy term. Okay, and this appears with a negative sign. Okay, because of the antisymmetry of the fermionic term. And here, because of this, there is an additional term in the potential energy compared to. So if you just naively wrote down like a second quantized version of this two-body potential, it would be just this V2 rho of R1 rho of R2. So V2 R1 R2 rho of R1 rho of R2. This is what you would have written down. Okay, as a second quantized, or as a many-body representation of, just naive many-body representation of this thing is that there's a density, there's a charge density here, and there's a charge density here, and there's a potential between them, and that's their contribution to the action. Okay, and if you put this charge density to be a delta function at R1 and a delta function at R2, this is what you will get. Okay, that is the idea. Okay, but this is a completely new thing which comes because of quantum mechanics, which comes because of the identity of particles. Okay, and there's a new term. So this new term can be represented in terms of the spin of these particles. Okay, Okay, so let me maybe just say, so this, the total thing here, this mod square, can be thought of as ordinary term In fact, okay, the way this is actually a little better. The way Landau-Lifshitz does it, they take the symmetric exchange and the antisymmetric exchange in one single shot. So you do this whole square thing here, and it becomes like this extra term becomes like plus minus. So ordinary term and exchange term. Okay. And this exchange term essentially so this is something that you would use for, let's say, spin 0 particles, okay, and the minus sign is something that you would use for spin 1 particles, okay. So you can write as a result this this object as, so this exchange term is an integral of this kind, which is V d to R1 d to R2, and let's say I call that thing as J, okay. You can show that this guy, this potential due to the exchange is given by minus half J 1 plus 4 S1 operator S2 operator, okay. This is just a clever device which says that for spin half particle it is plus sign, and for spin 0 particle it is minus sign, okay. This is just that. This entire thing here tells you that you can do this very easily, okay. So this 4 S1 S2 can be thought of as some kind of S1 plus S2 whole square, minus S1 square minus S2 square. These are all the elementary spin half particles. So this is just given by the Casimirs of spin half. So that's already known. So that's some 3/4 here, 3/4 here. And if the total spin is 0, then you get 0 here. If the total spin is okay, so I should say one bit of group theory here, which is that when you have an antisymmetric exchange of these particles, okay, yeah, maybe I should I was not clear enough here. Both plus and minus combinations, okay, are allowed combinations, okay. They are allowed combinations, okay, depending on whether the quantum numbers allow that, okay. So for instance, you can have if it is plus combination, you could have plus 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 here, okay. So that clearly gives rise to finally a spin 1 particle. Is that clear? I'm doing a symmetric combination of 2 spin half particles, okay. So I can take here symmetric combination of two spin half particles or an antisymmetric combination of two spin half particles, which will be spin 0. So, this will correspond to spin, total spin equal to 0. Here the total spin will be equal to 1. You have to make sure, of course, that it is consistent with exchange symmetry still. Is that clear? Is that clear to everybody that I can do this? So this symmetric combination of two spin half states I can actually do in the following way. Let us say that I have phi, let's say both are spin up, both are spin up, so if I have this exchange here, minus R1 phi plus R2. This is an antisymmetric state and it corresponds to a singlet. This corresponds to a spin singlet. Okay. And so these are the wave functions. This is the spin half wave function at R1, the spin minus half wave function at R2, and the flip. Okay. The quantum numbers remain the same, the position coordinates change. I could do the other way around also, that the position coordinates remain the same and I just flip this.
To explicitly think of this in terms of an example, how is it significant in the helium atom, for instance?
So, for instance, how do I construct so I can take, let us say that two of the 1s electrons, the 1s, so let us say this is like psi 1s plus and psi 1s minus R2. So, I am constructing the 2 electron wave function. I am constructing the 2 electron wave function. Like this. And I have this, for instance, will correspond to a spin s equal, total spin s equal to 0. Right? Right. If I am taking a singlet, okay, then plus minus and minus plus is the, well, if you wish I can write it this way. you know, this is what I have been writing so far as plus minus minus plus minus 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 plus, that.
Yeah, so are you trying to say that the radial, we have two parts, radial and spin. You can antisymmetrize either the radial part or the spin part such that the total thing is antisymmetric.
Oh, I'm now saying that the, you know, I'm not doing anything to the position part at all. Okay. So the maybe that's what I'm missing here. That's what I'm missing here. I must make the whole thing into yeah. So I cannot freeze these other guys. So I should really have L1 M1 and L1 M1 and MS1 and L2 M2 MS2. Okay, I can antisymmetrize in M1 these two guys and symmetrize in L1 L2 L1 M1, and this is the part which I was missing. Thank you. Okay, so then I can have the singlet state. On the other hand, if I symmetrize in S1 and MS2, then antisymmetrize in these two guys, then I have the correct thing. So no, I cannot ignore the other quantum numbers here. So I should bring that thing in here. So whatever that state is, so this is what. So let me say that yeah, thank you. Now I'm good. Okay, so I have two possibilities. Okay, so when I do this, okay, then I can take the same. Then I can take the same wave function like this, and this is a valid fermionic 2 fermion wave function. Okay, but when I want to construct the triplet, then I must have let's say this way, plus let us say I have both of them as plus plus, okay, as you have in a triplet. But now I have phi 1s plus R1 and psi 1s plus R2, okay, in which I have made the other quantum numbers different, okay, and I have antisymmetrized with respect to the other quantum numbers, which I am denoting by these different letters psi and phi. Okay, thank you. So, for instance, it could be by the LM quantum numbers, orbital angular momentum quantum numbers. So, I must do that, of course. This is and as a result I can get S equal to 1. Okay, very good. Yeah. So that is why there is this phi 1 and phi 2, which I had mistakenly dropped. So indeed phi 1 and phi 2 are they have the combined quantum numbers, the orbital quantum numbers and the spin quantum numbers, and I have to the total exchange of all the quantum numbers together must be antisymmetric. Okay, so anyway, the point is that once you have done that and you have written the exchange in interaction properly, you can show that the plus or minus difference can be thought of as this the 1 plus 4 S1 S2, okay, where these are the spin operators, okay, By the spin operator, I simply mean that this is the half integral representation of SU2. Okay, and depending on so this can be, as I said, this can be written as S1 plus S2 whole square minus S1 square minus S2 square. These are the single fermion Casimirs of spin half. So therefore, this is just 3/4, this is just 3/4, and S1 plus S2 whole square, depending on whether the total S, so this is the total S, depending on whether this S is a spin 0 or spin 1 representation, the value of this changes, and the value of this changes appropriately, so that if you have this, okay, for S equal to 0, for S equal to 0 it has a plus sign, and for S equal to 1 or S equal to 0 it has a minus sign, and for S equal to 1 it has a plus sign. Okay. So overall, the point that I wanted to say here is that there are interactions between the spins of these particles as well. Okay. So there is an S1 dot S2, and that says basically that the real conserved quantity is the total sum of this. As you can see from here, that S1 dot S2 can be written as S1 plus S2 whole square minus some constant. So it is this object S which is the conserved quantity. Okay, and so therefore this is this clear to everybody? This should really be done with the LM things properly put into account, and perhaps that should be done in some assignment. Okay, that the anti-symmetrization has to be correctly done by bringing in the other quantum numbers. But even with that, this statement remains true, that there is an exchange integral, and that multiplies 1 plus 4 S1 dot S2. Okay, which takes care of the sign here. Okay, so you take the square and the sign becomes plus or minus, and that plus or minus can be captured by this object. Is it clear? The strategy is clear? Okay. It's just this. This quantity is plus 1 for total spin equal to 0 and minus 1 for total spin equal to 1. Okay. So as a result, this plus minus sign gives rise to something which is called the exchange interaction, and that has a coupling between the various spins. Okay, so as a result, this statement which we said is not quite true, that it is 2L plus 1 into 2 to the power p. It is certainly not true, because that says that all spins, okay, S1 equal to plus minus, S2 equal to plus minus, S3 equal to plus minus, everybody have bunched together are at the same level. No. Okay. So various spins of the individual particles, okay, only their total, okay, is conserved. Just like various orbital angular momentum, only the sum of the various angular momenta are conserved. So this is for two particles I showed, but in general it is the sum of the spins of all the particles, A equal to 1 to p. This is what is conserved. Okay. So again, even the spin half representations of all these particles have to be tensored. Okay. And you take the various tensor product decompositions, and they get split into LS quantum numbers, and of course the ML, MS, and various other possible quantum numbers which are of the like the counterparts of the principal quantum number, and 2L plus 1 and 2S plus 1 is what the degeneracy is, corresponding to capital L and capital S. Okay. That is the story of the multi electron atoms. Okay. This is how the spectrum will go. Now here there will be some other LS. It will be given by 2L plus 2L tilde plus 1, 2S tilde plus 1, and so on and so forth. But these have other quantum numbers. As a result, by varying these other quantum numbers, perhaps the same LS values might keep appearing again. Just like it so happened that there is a 2p state, and there are 2p states and there are 3p states. Okay. So, the same L equal to 1 can appear many times, and here also the same capital L and capital S can appear other times also, because there are other quantum numbers here, which we have not kept track of. But this is the structure. The structure is that there will be degeneracies given by 2L plus 1 into 2S plus 1 from the angular momentum group theory. Is this clear? Okay. This is for non-relativistic. Relativistic corrections give rise to spin orbit couplings, L dot S. Okay. So, again, by going to a similar logic, if there are L dot S interactions, then it can be thought of as L plus S whole square minus L square minus S square. Okay. So, this object, okay, so let us say that I take some spin L representation here. So, this L square, so these are operators like that, and this, the value of this is given by some L into L plus 1, S into S plus 1, okay, which would have been by themselves conserved quantities, and these should have corresponded to exact, this should have indicated exact degeneracies of the theory, except that now I have this coupling, okay, which will split these things. Why? Because L and S are not independently conserved quantum numbers, okay, but this one is. Appearance of L dot S means that now the L plus S is a conserved quantity. Okay. Essentially, you can say that all of these guys, L dot S is like some LISI. You can rotate this. There are SI1, SI2. You can rotate all these guys by the same rotation matrix. And that same rotation matrix will be given by what is called J. Okay. Again, by using the same logic, that if you consider a given single SU2, okay, then, and that is this, every guy, okay, all of these are being rotated by the same one single SU2. Up to this point, there are two SU2s still, an SU2 which is rotating the LIs, and an SU2 which is rotating the SIs. Okay. So, we still have SU2 of orbit and SU2 of spin. Then I introduce the L dot S coupling, the spin orbit coupling, that is making this into just one single SU2, and that is called J. As long as you don't talk about nuclear degrees of freedom. Of course, nuclear degrees of freedom will make all, so the nucleons and so on and so forth, certainly. And so this is all in the approximation that the nucleus is infinitely heavy. And so finally, this is what the game is. So this 2L plus 1 and 2S plus 1 now will split. So this huge degeneracy that is there, okay, that will split according to the quantum numbers J. Okay. So what happens is that these guys, they split into this thing according to quantum numbers J. Okay. So you do an spin L cross spin. So earlier you had this 2L plus 1 times 2S plus 1 eigenstates, okay, which basically correspond to a tensor product representation of spin L cross spin S, and there are how many angular momentum representations are contained in this is L plus 1 all the way up to L minus S. Okay. These are the J values. All these J values are possible, and so corresponding to each of these J values you have some 2J plus 1 representation. So this is the final story, 2J plus 1 representations. Okay. So there's a small split if the relativistic if the spin orbit coupling, okay, which essentially comes from relativistic corrections, if that is small, then these are some small splits. So it is essentially this kind of degeneracy, but split in some small. So now you should really read Landau Lifshitz to get the values and so on and so forth. Okay, or Wikipedia articles. Okay, good. So now let me say that. Yeah, that's what I wanted to say. And of course, you can talk about interactions with external magnetic fields. Let us say that if you have interactions with external magnetic fields, then so this was written, the interaction of an electron, non-relativistic electron with an external magnetic field was given by for a single electron, let us say. So this, where I is the vector index 1, 2, 3. So any idea how the degeneracies will be split now? So that we arrived up to this. Now we put the system in an external magnetic field. What will happen to the spectrum? Sorry? Right. So now what will happen is that the so for a okay, so this is for a single electron. Okay. Now for the multi-electron system, you have to take all of these guys together and so on. So let us say for a single electron, what will happen? Suppose I take a single electron system in this in this thing. Okay. So this is the first. This is probably one of the first examples of symmetry breaking that you find is that let us say that this Bi is equal to 0, 0, B. Then what is the new residual symmetry? E1 or SO2. Right. So basically this R matrix, which earlier was earlier I was saying that the SI going to R, SI, R, SI was a symmetry where R is an SO3 or an SU2 matrix. Now this R in an SO3 representation can only be something non-trivial here, 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 like that. In terms of Lie algebra, it will be something non-trivial here, 0, 0, 0. Okay, so therefore, this is called symmetry breaking. This is called an explicit symmetry breaking because I am putting in a magnetic field, external magnetic field into the system, which I can dial. Okay, if I take it to be along z direction, then the symmetry, residual symmetry is this particular kind of thing, which is a xy rotation. Okay. So now, so this is called SU2 to U1 breaking, or SO3 to SO2 breaking. It's called explicit symmetry breaking as against spontaneous symmetry breaking, which we'll also see in a moment. So this is called explicit symmetry breaking.
Okay, so in those it is always the case that the vector that is breaking the symmetry explicitly and the vacuum expectation value are proportional.
If I do spontaneous symmetry breaking?
So you are breaking the symmetries explicitly, not spontaneously. Say B is not.
Yes, 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 yes. If this B is a vector, then this is the pattern of symmetry breaking.
As long as the group that I am breaking is SUN kind of,
Mm-hmm.
then the vector that is breaking it, like here it is B, it is proportional to the vacuum expectation value. So here you have gauged this residual symmetry U1 just by looking at
You are saying if I think of this as the dynamical field and this is the vacuum expectation value of B, that's what you were saying?
vacuum expectation value of S. Suppose you have
Vacuum
written down
expectation
the
value of
action.
S.
Suppose you have written down the action in terms of S,
Mm-hmm.
and then you are looking for classically the minimum of this action
Yes.
when calculated with respect to S, and you are basically you are trying to find three level vacuum expectation values of S. Then it will always be proportional.
Okay. Yes, yes, yes. Yeah, if you want to treat this problem semi-classically, which is possible to do for large number of electrons or large number of particles, then you can think of this as a solving the classical equation of motion. That is correct. Okay, but for a single electron, you cannot do that. For a single electron, you really have to solve the quantum mechanical problem, but that's not a big deal. With this choice, for example, it just becomes SZ or S3B. That's all. So you had some, so this is the only thing, and this gives rise to the usual split of 1s plus and 1s minus, that they get split, and so on and so forth. I leave it as an exercise what happens to multi-electron systems. Okay. Okay. I mean, it's clear that the spin degeneracy, the total spin degeneracy, okay, will be split again according to that. So here the total spin degeneracy will be split, as you said. Okay. Good. 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 So I have already mentioned Wigner-Eckart and the application of group theory and symmetry properties to time-dependent perturbation theory and transition probabilities. So we can find selection rules from Wigner-Eckart and also the quantitative measure of cross-section of those cases where indeed it is allowed. So remember what I said is that if you have some, so in time-dependent perturbation theory, going from a state I to a state F, okay, and if your interaction has, so this belongs to a certain representation alpha. Now I'm talking about a general group, and this beta, and this interaction is some other operator. So this is some particular kind of tensor, if you wish. This is some particular kind of tensor, if you wish, and this O of gamma is some other kind of tensor yet. So the existence or otherwise of a state of a matrix element like this, okay, is just a group theory question. and that is to say that alpha cross gamma cross beta, this should have a singlet in it, or alpha cross gamma should have a beta in it. All these are the same equivalent statements. And you can find, just to find the selection rule is enough to just do the Young tableau analysis, okay, to see whether this has a thing or not. But of course, the group theory part of this matrix element is given by Wigner-Eckart theorem. Okay, we have dealt with Wigner-Eckart theorem for SU2. Okay, and similarly there are by sort of you know, reasonably straightforward extension of that you have. Okay, so anyway, so this we have discussed. So that's one very, very important thing of. So in other words, staying within the same representations, if you change the particular state I within alpha, and if you change the particular state F within beta again, and within this class of tensor operators within gamma, you change this operator O. So then that change is given entirely by group theory. Okay, and the remaining dependencies, of course, you have to calculate by taking just the most convenient choice of I alpha and K, I alpha, I F and K. Take the most convenient choice of your representatives within a particular irreducible representation, compute that object, which is called a reduced matrix element, and from that on you can just okay, all right. So now let me just very quickly say what one of the biggest applications of group theory is to particle physics, and let me just quickly mention how that goes. So standard model, okay. Here there's a group. That group already is a product group, which is operative. Okay, so that is to say the Lagrangian has a symmetry under SU3 cross SU2 cross U1. This is something that is familiar to all of us by now. So we have done a lot of SU3, a lot of SU2, and U1 everybody knows already. Okay, so so the fermions of standard model, okay, they come in two varieties. They're called quarks and leptons. Okay, and so let me say okay, so quarks, let me use a general notation which is like, it gets a little cluttered. So this A is a fundamental representation of SU3. This I is a fundamental representation of this SU2. And U1 does not require an index, okay, it just has an assignment. And this P is something called a generation label. Okay, there is no symmetry understanding of this generation thing unless you go to some higher unified gauge series or something. They are just there. Okay, so this is generation. So what is the story for P equal to 1? For P equal to 1, so you have to have a fundamental. So let us say the fundamental of SU3 I call it a simple box, okay. And the fundamental of SU2, I call that another box. Let me see what kind of box I have given it. No, cross-hatched box this way. So this fellows, okay, so essentially I need a doublet here, right, because this is the fundamental of SU2. Fundamental of SU2 is a spin half representation, so I need a doublet. The doublet of this SU2 are explicitly stated by giving different symbols. So that is U and D. U and D. And this is written by carrying over this A here. Okay?
So A is the color index.
A is the color index. A is the color index. This is called weak isospin. These are all historical names. Weak isospin, and this is something which is called hypercharge, or sometimes called weak hypercharge. And this is color. This is color. So SU3 is color, SU2 is weak isospin, and that. And here, so I'll call the generators of these guys as TA, which will A running from 1 up to 8. These things I'll call tau capital I generators, which will run over 1, 2 and 3. And the charge of this U1 I would call Y. So what is the charge assignment of, what are the various eigenvalues of these generators in terms of the, so you know the UA fellows, they are given in terms of the, there are two Cartan subalgebras of among these TAs, okay, and they are assigned in some way to these things which we are not even going to bother about, okay. So these are a certain fundamental, so fundamental representation means what? This is something that we have called 3. So this A, belongs to what is called 3, okay, and so that's the fundamental representation. That's all we would note about this guy, okay. Can somebody tell me what the eigenvalue of tau 3 is? Tau 3 is the third generator of SU2 for U. Sorry? Plus half. So for U it is plus half, and for D minus half. Good. So those are the things. And now this is something that is given from physics. So the Y values are given by 1/3. Okay. Y values are given by 1/3. Okay. And it turns out that there is, this is the symmetry of the theory at very high energies, okay, but at low energies there is a symmetry breaking, okay. There is a symmetry breaking. This theory has, you know, potential wells, okay. At low energies you are in those potential wells. So in that, in a potential well like that, you have a breaking of this SU2 cross U1, okay, to just U1. But it is not this U1 that is preserved, okay. It's some linear combination of the tau 3 and this U1 which is preserved, okay. These things can be all generated. These are all played around to, you know, sort of fit phenomenology. So there is no understanding of these things from first principles so far, okay. But let me just tell you what the final conserved charge is. That's called obviously the electromagnetic charge. So this y divided by 2, okay. And now you can somebody do the math for me, please? So for you, tau 3 is this and y is that. So that's 2/3. You can perhaps say it from memory, and it's minus 1/3. Okay. So similarly, so this is the first generation. This P is a generation thing. This is the first generation. Then similarly, there's a second generation for which everything, all of these quantum numbers are repeated, and they are called. So this is U and D are up and down. So this charm and strange, and P equal to 3 is top and bottom. Okay, these guys are very light quarks. Okay, they are given by a few MeV. Okay, this is given by approximately 100 MeV. This is given by approximately 1 GeV, and this is given by almost 200 GeV. It's 170 or so GeV, and this BA is also a few GeV. Okay. So these guys are heavy. So there are some approximations in which U and D are really light compared to. So from the point of view, okay. So I'll come to that, and I'll come to that in a moment. So this story is true for. So it doesn't quite end here. The quark story. This is true for what are called the left chirality fermions, which have gamma 5 equal to 1. For the right chirality fermions, okay, they are they don't interact with the weak gamma 5 eigenvalue. So gamma 5 eigenvalue. So this story is true for the gamma 5 eigenstates, gamma 5 equal to 1, okay, which are called the left chirality objects. Okay. For the right guys, gamma 5 equal to minus 1, which one you call plus 1 and minus 1 is a convention. Okay. And which one you call left and right is also convention, but this convention is very well known. So this SU2, okay, acts only on the left-handed quarks, okay, and not on the right-handed fellows. And for them also, of course, it's the same story, but now tau 3. Can somebody tell me? Oh, sorry. There is no bracketing, so I should just write UA DA. So what is tau 3 on them? 0, because it's a singlet. Very good. 0. And the hypercharges are given by these. Now there is no need for the, okay, so here these hypercharges for U and D had to be the same, okay, because this guy and this guy are related by a symmetry. Okay, so if this is 1/3, this better be 1/3 also, okay, because they were related by symmetry. They were related by, and these two symmetries were commuting. Okay, so if there is a 1/3 there, this better be 1/3 also. Now this UA and DA, which are the right-handed fellows, there is no need for them to have the same hypercharge. Okay, so therefore they are different, and indeed they are invented in such a way that you get the same electric charge eventually. Okay.
This is just phenomenological assignment.
Indeed. So this is all this Gell-Mann's quark model, and good. And so that's the story with, and similar story with the other generations. Okay. And this matter, these quarks are called matter. All fermions are called matter, and the other kind of matter are the electron-like objects. Okay, electron and neutrino-like objects. They are called leptons. They are called leptons. They have one quantum number less. Okay, they don't interact with color. They don't have color charges. So the leptons have also a generation index, if you wish. They don't have this A business. They have I. So for the first generation, the top component is called electron neutrino, and the bottom component is called the electron, our friend electron. And for them, the tau 3 assignment, you can tell me that again. What are the tau 3 assignments? By the way, I have placed them. So again, it's half and minus half, of course. So it's half and minus half, and y comes again from phenomenology. But once I have assigned some quantity here, I must put the same hypercharge here as well. Okay, so it's -1 and -1. And of course, this -1 is actually invented so that the total charge, the electromagnetic charge, is 0. Okay, so the electromagnetic charge, again by the same formula, is given by 0, and this fellow is -half, and you do half of that, so that's -1. So some sanity eventually prevails. Okay, that at least the electron properties we have got correctly, and yes. Sorry? This SU2 is the same. It's the same. Oh yeah. The name is also, well, it should be called the weak SU2. You know, this isospin is a historical name given to something which I am coming to in just a moment. Oh yeah. So this tau 3 is the same as in here, this guy. Okay. So the weak interaction indeed acts on, so these guys do act under weak interactions with each other. The hypercharges and they have these charges and so on and so forth, but they are not colored. Okay. Now, so there's a lot of story that, of course, and that's the story of the fermions. Oh, and then this is also about left fellows. Gamma 5 equal to 1 and gamma 5 is equal to -1 are the right moving guys. So whether there are right moving neutrinos at all or not, okay, that's yet uncertain thing. So let's not talk about that. But there are right moving electrons, and so these guys have the following assignments. Once again, the right-handed, sorry, not right moving, right-handed, okay, chirality. Okay, so these right-handed electrons, they are not acted on by weak interactions. So their tau 3 eigenvalue is 0, and their this y, the hypercharge, is taken to be -half, so that the electromagnetic charge is -1. Okay, that's the game. And then, of course, there are the gluons which are in the adjoint of SU3, and there are weak bosons or Z bosons, and then there is the U1 boson. So this is in the adjoint of, so there are this G A mu and the weak bosons are you can call it maybe W I mu I running over 1, 2, and 3. And then there are Higgses and so on and so forth. Okay, so the this. But what I wanted to tell you is that suppose. Okay, so now I already told you that there is a symmetry breaking that happens in the weak sector, and SU2 cross U1 is broken. However, there is a global SU2 still in the Lagrangian. There is a SU2 symmetry which relates it's directly related, of course, to this the SU2 gauge symmetry is broken. Okay, but there is a global SU2 symmetry which is called a flavor SU2 symmetry. Okay, that is there, and it connects U and D. Okay, and that symmetry is of course broken a little bit. So let me tell you why it is broken. Because of the, so by the way, when I wrote these masses, when I wrote, okay, so I didn't write them, I mentioned them. These masses also appear after symmetry breaking. Okay, to begin with, okay, all quarks are massless. In the QCD Lagrangian, all quarks are massless. There are no mass terms at all for. Then you turn on these Higgses, you turn on the Higgs potentials. The Higgs potentials have, the Higgs has some potentials. You go into them, the Higgses get vacuum expectation values, and because of some Yukawa couplings, you pick up masses. Those masses are such that the U and D have masses which are very close to each other. They are also small, okay, but they are also very close to each other. So there is a flavor SU2 symmetry. Flavor SU2 symmetry, okay, which in old days it was called isospin, which is some symmetry which related protons to neutrons. Okay, people didn't know about quarks in those days, but people found that in nuclei, okay, there is a lot of symmetry between protons and neutrons. Okay, it's almost like the proton is a charged version of the neutron. Okay, the masses are very similar. The strong interactions didn't seem to make much of a difference between the strong interaction between protons and neutrons and neutrons and proton, etc., etc. Okay, so that symmetry is called isospin, and we will do yes. Yes.
So, is there any connection between this flavor symmetry breaking and the confinement? They happen almost at the same scale.
Chiral symmetry breaking. Okay, so there's
relation between chiral symmetry breaking.
Okay, yeah. No, in principle they are independent, and certainly. They don't have to be in the same at the same temperature, but in fact there are indications in the string inspired models that the deconfinement transition happens first, and then the chiral symmetry breaking transition. Okay, so what we are talking about here is that the
the confined phase that can't be broken or something? I'm asking because I'm not sure of this.
There is no strong statement, but I think there is some sort of indication that in the confined phase you have unbroken chiral symmetry, and you have to first go, or maybe at the same time, okay, you have to go to the deconfinement transition, and chiral symmetry breaking happens, or slightly later, first deconfinement and so on. That I can tell you. So anyway, the point is that let us do the following group theory exercise. Suppose I want to, so there's a lot of so there are various things I'm not telling you. So for example, this interesting story of chiral symmetry is that the U and D really have very small mass, and everybody has to begin with, everybody has zero mass. Okay, all quarks have zero mass. All leptons, everybody has zero mass, and so it's because of so now there are two ways of mass generation of composite particles like mesons and baryons and so on. One is through QCD, okay, through formation of condensates and so on and so forth. That actually accounts for most of the mass. I mean, the larger fraction of the mass generation happens through QCD effects, okay, condensates. Okay, there's some I can tell you there's a I mean these are like the Q bar Q condensates. Okay, you can take vacuum expectation values of Q bar Q can be generated by some very interesting dynamical effects. Anyway, so and Higgs. Okay, so the stuff that people say about Higgs, that all our masses are due to the Higgs particle, that's wrong. That's very wrong. Okay, our masses, we are made of baryons, and these baryons get most of their masses from the QCD phenomena, which has nothing to do with Higgs. Okay, so and anyway, the point is that yeah, good. We will ask the following question. Okay, so let me tell you first the following fact, that all states in this theory have to be color singlets. Color non-singlet states are not allowed states which can live freely in nature. Okay. All states have to be color singlet states. Okay. This is a phenomenon called confinement. Okay. Color is confined. Whatever you can see outside from long distances are colorless objects. Okay. So they have to be color singlet. Yeah, they have to be color singlets. So let's try to construct our group theory knowledge of constructing color singlets. So what we mean by this is that of course a single quark state cannot be a color singlet because it belongs to the fundamental representative. It has an index. Okay. How do we construct color singlet states of let's say taken only out of quarks? Okay. One possibility is Q bar Q kind of states. Okay. Let us leave it. So that's a simpler exercise. So we'll leave it at the moment. Okay. Another possibility is so Q bar Q. How does the group theory work out? That is color singlet, because Q bar Q has 3 bar and 3, but we have so now we are discussing how to construct color singlets. So one possibility is Q bar Q kind of object. Okay. Of course, you have to show that this 2 particle state, okay, is somehow, it behaves like a 1 particle state. It's a bound state. Okay. The binding energy, etc., has to be computed. Okay. And it has to be that otherwise a 2 particle state, like you and I are 2 particle states, but we don't always move together. I mean, so Q bar Q as what? Largen, yeah, some simple Largen theories can show this, and yeah, lattice. You know, you can compute 2-point function of q bar q kind of states and show that, you know, it has a reasonably narrow pole. Okay, so the pole of that 2-point function of this composite q bar q and q bar q here, okay, if you find that, you know, it has a sharp pole, okay, then it's a well bound state. Otherwise, you know, if they are very shallow states, then it will be like this. It's almost like a 2-particle weakly coupled. So this is a strongly coupled system, and it has a good binding energy. Okay, so that's, we are not saying anything about that here. We are saying only about group theory. Okay, so this, how does the group theory work? That it's a color, it can give you a color singlet. Is this that 3 cross 3 could be 8 plus 1, but of course these are fermionic states. Okay, so just the same exercise that we did for the exchange interaction. Okay, we have to make sure that all quantum numbers exchanged together, okay, gives rise to a minus sign. That we have to do. So that you have to do. So I leave this as an exercise. Let's do baryons. Okay. So that was q bar q. Is there any other way of getting a singlet from combining threes, just threes, no 3 bars? Yes, exactly. So I can just take all of them on top of each other, and that's a singlet. This is SU3. So this actually is a nothing representation. It's a singlet representation. So therefore, 3 cross 3 cross 3 does have singlet. Okay, is it clear to everybody? So 3 cross 3 has this representation and this representation, clearly by Young-Tableau methods. This you can work out by the Weil dimension formula that it's actually a 6-dimensional representation, and this is 3 bar. So 3 cross 3 gives you a 6 and a 3 bar. 6 is the symmetric one and 3 bar is the antisymmetric one. Now I have another 3 coming in, so clearly 3 bar cross 3 has a singlet in it, so we are done. Okay, so therefore 3 cross 3 cross 3 antisymmetric is a color singlet. Okay, these things are called baryons. Okay. Now, so therefore, in terms of the quantum numbers that we wrote here, you can write epsilon ABC and Q QP and QP1 A I1. Okay, so that's too much. So I have to antisymmetrize in all the colors. Okay, and overall I have to ensure fermionic antisymmetry. Okay, so the wave function that I write in that, if I have something like psi A and generation level, or let's forget about generation level. Let's try to do it within every generation. So psi A I, and there's also the Dirac index and the space-time index. So all of these guys exchanged together, okay, and I have 3 such fellows. Between any pairs, if I exchange all these quantum numbers together, okay, I must get a minus sign. Okay, so the overall wave function, the 3-particle wave function, must be of that kind. Once again, the 3-particle wave function, I am assuming that it will have a bound state. It will be a bound state. Otherwise, constructing a 3-particle wave function is not a big deal. okay, but it's the dynamical significance that we leave now. So, but how does the group theory work out? So, ABC, okay, so this is B, J, beta and Y and C, K, gamma, Z. This is the full thing. So, I must ensure that since they are already antisymmetrized in terms of ABC, okay, they must be symmetric with the interchange of the other quantum numbers. Okay. Now, let us say that I choose the same isospin species here, namely I choose I equal to 1, the upper fellow, namely U. Okay, so I symbol is gone, this is gone, K is gone, and ABC I have already made them totally antisymmetric. So, I can take them to be 1, 2 and 3, and I can think of these as, you know, cyclic permutations and with things. So, I'll forget about these guys as well. So, I must have therefore alpha, beta, gamma, and this x, y, z, remember that this is our this is what something that we call alpha, beta and gamma. X simply labels the Hilbert space of the first slot, y labels the Hilbert space of the second slot, and z labels the Hilbert space of the third slot. Okay. So, I can write this object as just this, alpha, beta, gamma, right?
Bound state thing is, there is another thing that you need to insert.
Oh yeah. I am assuming that there, so that's a very hard proof. I am not going to that at all, but I am just saying that how do I construct a color singlet? Okay. So, after all this, it just means that I must construct symmetric combinations of alpha, beta, gamma. In particular, for instance, I can choose this to be upspin, upspin, upspin. Okay. So, that should be one of the possibilities. So, therefore, this must be in the spin 3 half representation. Okay. So, spin 3 half representation. And I have taken all of them to be U. So, what is the total charge of this? Plus 2. So, the total charge is plus 2 and the spin is 3 half. This animal is called a lambda baryon, lambda plus plus. If you want to construct a spin half baryon, okay, you must not have U. If you have all of them to be U, then you are forced to have alpha, beta, gamma symmetric. You are forced to have a symmetric tensor product. Okay. So, you are forced to have all the SU2 fellows joined up like this. That is spin half. Okay. In order to have spin, that is spin 3 by 2, and in order to have spin half representation, you must have at least one of these letters different. Okay. So, that is UUD or UDD. Okay. Now, here there are two kinds of objects that you can have for UUD. One,
What about generation?
you mean what about isospin? This SU2, yeah?
I am saying that you are taking from one generation only.
Oh yeah. So okay. So I'm just I'm taking only one generation now, but I'll tell you about something called an SU3 flavor symmetry. That's the last thing that I will say. Okay, so this is something that is we constructed from group theory a possibility of a particle like lambda plus plus. Okay. Now UUD can have two kinds. One is you can start from here and you can take the lowering operator of the weak SU2, okay, on this, okay, and so this let me rewrite this. So this is U plus and U plus. By the way, when I construct the spin 3/2 multiplet, of course I should complete the multiplet by applying J minus to all of them. Okay. So like if I start from plus plus plus, at the next step it will be plus plus minus, plus minus plus, blah blah, etc., etc. And now I can apply this tau minus operator to see what I get. So I will get some U plus, U plus U plus D plus. What does tau minus do to U? Is the lowering operator of the SU2, okay, the weak SU2. So therefore, the isospin SU2. Okay, so we should probably be careful our things. So it works by it acts by Leibniz rule. So it will be some UUD plus UDU plus DUU, but all with plus 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 plus. So that will be again a spin 3/2. The multiplet of the spin I can again complete by applying J minus to all of them, okay, and or S minus. In this case it's only intrinsic spin. We are not talking about any orbital angular momentum here. And this object has, okay, what's the charge of this? One. So this charge of this is 1, and this object is called lambda plus. I can apply tau minus once more on this, so that will give me UDD in various combinations. Okay. So 1U and 2Ds. This thing is called lambda 0. Again it will have S equal to 3/2 and this way, and once more I'll get DDD, okay, that will give me lambda minus. So this was charge 0, UDD will have charge 0, this will have charge minus 1. Okay. These are objects which can be visible in the real world, okay, and they all have integral charges. Okay. So that's the amazing thing about this group theory, that although the basic elements are quarks which have fractional charges, but the stuff that whenever you construct a color singlet, the electromagnetic charge of these things are integral. Okay, but these are not the baryons which have S equal to half. Okay. For S equal to half, certainly I need at least UUD, okay, but this combination will not do. What should I do to this? I should take one of them to be minus, and then take various combinations to make this a legal fermionic state. That is to say, the color has already made sort of played the role of so it's basically taken care of the antisymmetry. I have to make sure that in the other quantum numbers it's all symmetric. So I should take this, yes.
In the UU case, we could have applied S minus, where we could have gotten symmetric combination of spins given there, right?
In terms of S?
Yeah, instead of tau minus, apply S minus.
No, but that will be part of this multiplet. you know, basically it's all given by.
U won't be changing, right? U's remain U's.
No, U's will remain U's. But I'm saying that since that state will be obtained by applying an S minus on this.
No, not that one. The previous one. U plus U plus U plus.
On this? Yeah.
Apply an S minus on that.
Yeah. If you apply on S minus on that, okay, you will get some U plus U minus plus two other terms like that. This will all be part of the lambda plus plus multiplet, right? Similarly here, if you start from this guy and apply S minus, so there are two things going on. One is the you know, weak lowering charge, another is the SU2 lowering charge, I mean the spin lowering charge. So, so this, whatever you are getting from here, that will be part of the lambda plus plus multiplet, this is part of the lambda plus multiplet and so on. But for spin 3 by 2, you know, it would be plus plus. You might say that how come from here I can't apply an S minus to get this, okay. But you know, this is the, if you apply S minus from here, the combination of signs that appear here, okay, will ensure that that object is still lambda plus plus multiplet, okay. Sorry, no, that anyways will not happen. If I just add apply S minus to this, I'll get one more minus sign, okay. But you might say here that suppose I have constructed this lambda plus multiplet, which is U plus D minus and no, this is what I got. For spin 3 by, for spin half, I should take these guys to be U plus D minus and whatever else is needed in order to make this a symmetric combination of the quantum numbers, okay. The letters U and which is the weak isospin quantum number and the spins.
What happens
Okay.
if you actually parity on this upper state?
If you yeah, I think these guys are all, this is all being done on the, yeah, this analysis probably you can do all on the left-handed, no, hold on. No, this is after the mass generation and so on and so forth. No, so this is about the Dirac fermions themselves. No, this should all be you know, the standard Dirac electrons without any. What I am saying is that what is the yeah, I don't know. I don't, but it yeah. Let me not say any. Let me not say any. Okay, good. So so this fellow and the suitable linear combination. Let's check out what the property of that is. So S is equal to half by construction, and charge is equal to 1. Okay, and it's a baryon. Okay, any idea what this object is? It's a spin half baryon with charge 1. What? Any guesses? What? Proton. Yes. This is the proton. Okay. And there's another spin half object which is UDD. So, you can take UDD, okay, and again in order to ensure that it is spin half, you should take two of them to be plus, the other one to be minus. This plus minuses are up down labels, and that's spin equal to half, and then the charge of that would be equal to 0. So, by now I guess you guys can figure out that that's the neutron. Okay. So, that's the neutron, and clearly they are related by this flavor SU2 symmetry. So, this is the original original notion of isospin. Okay. Now, we can understand this as that we start with this stuff. There's a gauge theory here. We had a symmetry breaking, and we are left with some flavor SU2 symmetry. This game is played on somewhat bigger scale, in which people say that okay, up, down and strange are both light objects, and their masses are taken to be similar or 0. 0 is the approximation which is called the chiral limit, in which these masses are all 0. And in that case, when you ignore the mass differences, they are all called light quarks between up, down and strange. Then there is a bigger symmetry called flavor SU3, okay, involving U, D and S. Okay. So, this U, D and S is called an SU3. If you look at the Lagrangian, indeed you can invent such an SU3 symmetry, and in particular for masses, if you say that the mass term is like this with the same mass for all of them. So, clearly this term is invariant under SU3, and you can invent the in the symmetry broken phase, you can invent such a Lagrangian, such a symmetry. It's called the flavor SU3. Sorry, what?
So this is U3, you can say, but you are saying.
Oh, no. This is, yeah, this does look like U3. But yeah, okay, that's true. The SU3 part of it, yeah, there is a U1 part of it, which is like it's counting the number of U, D and S. Yeah, I don't know what exactly that U1 is doing, but yeah. So anyway, so there's a lot of a lot of the somewhat old time phenomenology, and a lot of chapters of Georgi. That's about the classification of the known baryonic particles and mesons in terms of that SU3. It's only an approximate SU3, but there are you can arrange the baryons and mesons, etc. in terms of these animals. Okay, so this ends my first half of this one.